The Stokes polarization mode enables partial polarization to be represented. This allows the analysis of systems that polarize natural light to some extent, as well as systems that depolarize light. In the past, ASAP models had to be either unpolarized or fully polarized. Not anymore. A common way that natural light becomes polarized is by interaction with a simple interface, like glass. So in this model, we're interacting with a simple glass interface at the Brewster angle. The Brewster angle is special because it fully polarizes the reflected ray. So let's take a look at the Poincaré Sphere tool. Let me change the background to make this a little clearer. And I'll zoom in a bit. So we have 3 points here. At the center is the original source point. That is unpolarized light coming into the system. Just next to that is a transmitted ray, which has a flux that is 92% of the incident ray. Just note, the flux is 1 here. The flux is 0.92 here. So the transmitted ray is slightly polarized and has a flux that is 92% of the original. On the surface of the sphere, over here on the equator, is the reflected ray. Its flux is about 8% of the original flux, and it is fully polarized. How do we know it's fully polarized? Well, by physics, we know that it's at the Brewster angle. That I set that up specifically. But by ASAP, how can I investigate that? The degree of polarization slider here works in the Stokes mode to show us degree of polarization information. So if I slide it down to 90%, fully polarized rays disappear from representation in the Poincaré Sphere tool. If I slide this down further, I should eventually see the transmitted ray point disappear. So we're at 20%, it's still there. We're at 10%, it's still there. And finally at 0% DOP, or degree of polarization, we're left with only the original source point. Let's take a look at the output of a list ellipse command, which shows these 3 points. So you see, we have a degree of polarization entry here, and the original ray has a degree of polarization of 0. That's this one. The transmitted ray has a degree of polarization of about 0.085. So when we go to 0.1, it should reappear, and it does. And as we go up to 1, we should get back the reflected ray. And indeed we do. Now let's take a look at a slightly off Brewster case. So we've made the angle slightly larger so that we're no longer exactly at the Brewster angle. And let's go back and set this up so that we can see this just as we did before. So we zoom in and we notice it appears that the original ray and the transmitted ray are a little further apart than they were in the previous case. And the reflected ray is no longer on the equator. That means its degree of polarization is no longer 1. Its degree of polarization is something less than 1. So we can use the DOP slider to investigate this, but first let's look at the output of list ellipse again. The original ray has a degree of polarization of 0. It's completely unpolarized. The transmitted ray has a degree of polarization of about 16%, or 0.159, and our reflected ray has a degree of polarization no longer 1, but about 0.77. So let's just verify this with the degree of polarization slider. We come down to 0.9, 0.8, it's still there. At 0.7, the reflected ray point disappears. As we come down to 0.2, we still see the transmitted ray point, but when we go to 0.1, it should disappear, and it does. And when we go down to 0, the original source point is still there because it's at 0 DOP, and we don't eliminate that with the slider. So this is a really good indication of the value of partially polarized tracing modes as the Stokes mode. Just to show you very briefly how we set that up, it's actually pretty simple. Polariz mode Stokes, that's short for polarization mode, and that enables us to do partial polarization analysis. Now let's look at a ray trace in Stokes mode that involves more arrays. Something that looks a little more like a full system design. We have a polarization source here that is randomized with a randomization of the degree of polarization from 0.69 to 0.81. So not only is it polarized, but it's polarized in a partial way. Its degree of polarization is varied along with the polarization states. And this is the result of having a system with 3 sources with radically different polarization states and different degrees of polarization. At the North Pole, we have right circular polarization and elliptical states near it. At the bottom, we have some elliptical states near left circular polarization, but not exactly on it, thus the hole around the pole. And around the equator, but inside with a degree of polarization less than 1, is another group of rays, another source. And we have some flux variation and thus some color variation in each of those 3 populations of rays. So what do we expect to happen when we use the degree of polarization slider? Well, 2 of the 3 sources are fully polarized. So when we go to 0.9, those 2 disappear. Let's now zoom into that center population and pay attention to what happens to it. So we vary between 0.69 and 0.81. So when we go to 0.8 degree of polarization, we expect some of this population to disappear. And they do. If we go to 0.7, more disappear. But there are a few left because this actually started at a degree of polarization of 0.69. So when we go to 0.6, the rest disappear. And of course, nothing happens as we go further down because all of our rays have already disappeared. So now let's zoom out a little bit and see what happens as we step back up. We go up to 0.7, a few rays come back around the middle. At 0.8, most of the rays come back. At 0.9, all of the rays in this partial polarization group come back. And finally, at a degree of polarization of 1, we have all our rays back. So this illustrates again how the degree of polarization slider can be used to learn things about the population of rays and their polarization states, particularly their partial polarization states.